Okay, so we've done this problem of working out the right can extension. Um, the next thing is to work out the left can extension. Um, so um, some of this stuff wants like more rigorously doing, but um, I think hopefully the full layout is all here. So basically, what we're after is to understand this. So once again, we have a functor k from a category M to a category C. And we have this set to the power of k. Now we want to get the left adjoint of it, which we call lan k. So to do this, we focus on trying to get the left can extension, L comma eta dash, of this t in set to the power of m along this functor k from M to C. And this is basically just an initial morphism from t to set to the power of k. So this is our kind of picture. And yeah, what we're really after is this initial morphism. This initial morphism L comma eta, which is an initial morphism from t to set to the power of k. So that's what we want. Now, as usual, we start by doing loads of setup with for constructions with comma categories. This is a bit novel because I think this is the first time I've talked about how to do a certain kind of arrow lifting when it comes to left can extensions, but it's basically just the same idea as what we were doing with the right can extensions, just sort of dualized. Anyway, we have an arrow G from an object C to an object C dash in the category C. And we're interested in calculating L of G, and of course its source L of C and its target L of C dash. Now this is going to be an arrow in set. Why? Well, because L is a member of the category set to the power of C. So we want to work with comma categories. So k downwards arrow C is this category with objects as pairs M comma F, where F is an arrow from K of M to C for an object M of the category big M, and an arrow from M comma F to M dash comma F dash is just going to be an arrow U from M to M dash in category big M, such that this kind of triangle commutes. There's also going to be a projection functor P from K downwards arrow C to M, and that's going to send this arrow U in the arrow in the comma category to this arrow U from M to M dash. We also have this constant functor here for an object, well, for a set A. It sends everything in all the objects in K downwards arrow C to the set A. So this is a constant functor delta A. Now another thing that we have, and this is the novel bit, is I mean, we're always thinking about this arrow G from C to C dash because this is really what we're trying to calculate L of G of. And one thing that's going to come in quite useful for doing that is that we actually have a functor which we could call K downwards arrow G. That's a functor from comma category K downwards arrow C to the comma category K downwards arrow C dash. And what it does is it basically sends M comma F to M comma GF. And you can see why that works from this picture. So Okay, that's all we need for a setup. Now, L of C is going to be the apex of, so L of C is a set, right? And it's going to be the apex of the colimit cone of T after P. And so this is like, I've starred it because it's like the first thing that we really are going to be using for this kind of construction. So this is just basically standard construction of a colimit of the apex of a colimit of a functor into sets. Okay, so basically we have this sum thing here. So this is basically the set of all t. Well, I could say it like this. It's the set of all t m comma f such that t belongs to t after p of m comma f, where m comma f is some object of the comma category. There we have it. So it's like a load of dependent pairs, kind of like a sigma type. Although I might have swapped around the order of the indexing, but yeah, I'm thinking of the elements as tagged like this. So basically, this something here is like the coproduct or disjoint union of a load of sets. And we can think of it really as built with the functor T after P, but because the P is like a projection that gets rid of the F, it's like a sum of T of M. So L of C is that sum set, but quotiented out by this equivalence relation squiggle squiggle. So squiggle squiggle is a minimal equivalence relation such that for any arrow U of the comma category, like this, and if we take this element T of M comma F, any element in here, in this sum, of course we're going to have T is belonging to capital T of M. Well, we're going to have that T of M comma F is squiggle squiggle equivalent to the thing we get by doing capital T of U on T with its comma M dash comma F dash. So, I mean, yeah, this is just the standard form of the apex of a colimit of a functor into set. But like basically we can just think of it as form this coproduct of all of the objects in our diagram and then draw all the little arrows showing how everything gets mapped under the liftings of all the functions in the diagram, and then identify anything that's linked by arrows. And so the set of connected components then becomes L of C, and that is basically what this is. Okay. Now it's a bit weird because the functor we're lifting under is that we're lifting the arrows under is T of P, but like T of P basically T of P of U is basically T of U because P just doesn't, like when we do this projection. You see basically we're sort of sending U to U. It's just a sort of low dimensional U in some sense. Okay, fine. So that's L of C. So yeah, this is our first sort of noteworthy point because we're saying how this functor we want to find works on objects basically. So yeah, L of C is the set of equivalence classes of this sum under the equivalence relation squiggle squiggle. Now, for an element of this sum, so say t comma m comma f, so this would be a little t belonging to capital T of m. When we wrap that in square brackets, we mean the equivalence class that belongs to, or if you like, the connected component, if we're forming that graph linking stuff that gets mapped to each other by lifted arrows. So this denotes the equivalence class of, under squiggle squiggle that t comma mf belongs to. So that's basically the form of this apex of colimit, cocone. The actual colimit cocone is denoted by phi. This is going to be a natural transformation from t after p to L of c because it's a colimit of t after p. Also, we want to, because we're interested in like this arrow g from c to c dash. So we sort of use similar notation. We use delta dash to denote the constant functor that comes from this common category k downwards r c dash. We use p dash to denote the projection functor that goes from this common category k downwards r c dash to m. And then we say that the apex of the colimit of t after p dash is phi dash. Yeah, and so here's the thing. We've already described, so we have this functor g from c to c dash. We've said how this gives us this functor k downwards r of g from k downwards r of c to k downwards r of c dash. And therefore, if we raise this to the power of set, it kind of goes in the opposite direction. So it'll be a functor from set to the power of k downwards r of c dash to set to the power of k downwards r of c. And it turns out that if we have this limit cone phi dash of t after p dash, and we do set to the power of k downwards r of g on it, well, let's call that natural transformation mu. Turns out that's going to be a natural transformation from t of p to delta of L of c dash. And so here it is. And in fact, we can use that to define L of g. So in particular, we've now got, this is the limit cone. This is sort of this is the limit cocone of t after p. This is a kind of candidate cocone of t after p. And therefore there exists this unique arrow mu dash from the apex of one to the apex of another, in particular from L of c to L of c dash, which is such that it makes this triangle commute. So we've got the delta of mu bar after phi equals mu. And we define L of g to equal this mu bar. So all we have to do now is sort of calculate this intermediary arrow associated with this kind of limit, colimit, cocone. So here's a reminder of how that works. Well, firstly, how does actually phi work? For an object m comma f in k downwards arrow c, we've got that phi of m comma f is an arrow from t of m to L of c. And the way this is going to work is it's going to send a little t in capital T of m to this kind of wrapped up thing. So we form t comma m comma f, and that's going to be in the sum. And then we wrap it in square brackets to find the appropriate equivalence class, and that gives us our element of L of c. Now mu, on the other hand, we've already said it's defined as set to the power of k downwards r of g operating on phi dash. So we can write that as phi dash horizontally composed after the identity of k downwards r of g. and that's going to have a component. The MF component of that is going to be basically this, which we calculate to be phi dash of M comma GF, and indeed that M comma GF is going to be an arrow of the comma category K downwards arrow C. So that's good. And that component it goes from T of M to L of C dash. Okay, so now we want to define mu bar. Okay, so we want to get this unique intermediary arrow. So we've got now this mu as an arrow from TP to delta of L of C dash, and we want to find mu bar. So the way this works is that if we basically pick any equivalence class of the sum of the left-hand side, so if we pick any k in L of C, we want to find L of G of k. So if we just pick any, and it doesn't matter which one, if we just pick any t comma m bar comma f bar in this sum, and then we have which has the property that k is equal to the equivalence class of this thing. Then if we just do mu of m bar comma f on this t, I mean this t here is going to be in t of m bar, and then doing mu of m bar comma f bar is going to give us something in L of C dash, and that's what we define as L of G of k. So it's as pictured in this diagram. Now in this case, we know how mu works. So mu of m bar comma f bar of t is going to be phi dash of m bar comma g after f bar of t. And we know that just sort of injects, appends, and finds equivalence class of. So basically doing phi dash on this t here gives us t comma m bar comma g after f bar, and the equivalence class of that. So that's how L of G works basically. And I say it a bit more here. So I've starred this because again, this is saying how L of G works. I'll just leave this on the screen. You can pause it. This is like a more explicit description, but I'm not sure it's actually cleaner. But right. So the next thing, so we're after this left can extension. So we wanted L comma eta dash. We found L. We found how L works on objects and arrows now. The other thing is eta dash. So for an object n of this category M, consider k downwards arrow k of n. Let this be let phi double dash be the colimit of the functor t after p double dash, where p double dash is a projection. Of course, the apex of this colimit cocone is going to be L of k of n. Now notice that n comma identity kn is going to be an object of k downwards arrow kn. That's because we've got this kind of thing. That's going to be an object, okay, of this comma category. What we do is we take the n comma identity k of nth component of phi double dash. That gives us the nth component of eta dash. And we can find out indeed that is an arrow from t of n to L after k of n, and that's what we can define as eta dash of n. So now we've also got and we can do this for any object n of a category m. So this gives us our eta dash. So now we have and so yeah, let's just calculate how this eta dash of n works. So it's going to be a function from t of n to L of k of n, and it's going to send t in capital T of n to t comma n comma identity k of n, the equivalence class of that. Okay, so that's fine. So now we've got we found our L comma eta dash, which is forming this left-hand extension of t along k. Now, the next thing we're interested in doing is understanding lan k in its totality and the adjunction. So the unit, a tth component of a unit is just going to be this eta dash, okay? So we could, if eta is the unit, we could say that eta subscript t is eta dash. And also this tells us how lan k works on objects, because lan k is going to send an object t to the L that we've just described, okay? Anyway, we also want to figure out how lan k works on arrows. And again, this is all a little bit up in the air because it's sort of something I just basically guessing, but it has the right formula. I'd be very surprised if it's wrong, as long as I've got all the forms right, because it's like just sort of like the jewel of the RAN-K thing that worked. But basically, say we have an arrow alpha from t to t dash in set to the power of m, then lan k of alpha is this unique arrow in set to the power of c, such that lan k of alpha after identity k makes this square on the right commute here. So I think the way this works, I mean, what we're after, this is a lan k of alpha is an arrow of set to the power of c. So if we pick an object c of category c, then the cth component of lan k of alpha is going to be a function from L of c to L of c dash. So if we pick a k in L of c dash, it's going to send that to some k dash in L of c dash. Now the way that we determine this k dash is that what we can do is we can pick any t comma m bar comma f bar in this sum here, this sum over m comma f of t of m, basically, that has the property that the equivalence class of this t comma m bar comma f bar is k. And then the way that we get this k dash, or if you like, the way that we get lan k of alpha subscript c of k, is that we take our t here, which is a member of capital T of m, and then we do alpha m bar on that t, and that gives us that gives us, right, so we've got this T here, which is going to be a member of capital T of M bar, and then we do alpha M bar of T. That's going to be a member of capital T dash of M bar, and then we add on the M bar comma F, bar, and that's going to give us something in the sum, and then we wrap that in an equivalence class, and that gives us something in L dash, where here this L dash is going to be ln k of T dash. So it's basically going to be having this kind of form. I mean, we need to wrap this in equivalence class brackets, okay? So that, well, okay, I'm giving it a dash there because this thing's a bit different. Maybe I could put a dash there as well. But yeah, and this is basically saying how ln k works, I think. I mean, once again, I can check that it actually does make this kind of thing commute. But yeah. So that's it, I think.